And if we were to think about which one of these is better, it turns out that it's the same in terms of formal charges, so that doesn't help us out. So we need to go to this second case where we're instead going to think about electronegativity, and we want to think about which atom is the most electronegative. So in this case, we see that our formal charge is negative on the nitrogen. In this case, it's negative on the oxygen. Which of those two is more electronegative? The oxygen. So you should be able to look at your periodic table and see this, or also I've written the trend here. So that means that the more stable molecule is going to be this molecule here, which actually puts the negative charge on the more electronegative atom. So this is our lower energy structure. So these are the different ways that we can actually go ahead and use formal charge when we're choosing between different types of Lewis structures. So one last concept that I want to introduce is this idea of resonance. And resonance is the idea that sometimes one single Lewis structure does not adequately describe the electron configuration around a given molecule. So instead, you need to draw two different Lewis structures to describe that more appropriately. So let's quickly go through the Lewis structure for ozone. I have the skeletal structure written up there. I've written it twice, and you'll see why in a minute. It's easy to write the skeletal structure because it's all oxygen. We don't have to worry about what's going to go in the middle. In this case, we're going to have 3 times 6 for valence electrons, 6 valence electrons for each oxygen. So we have 18 total valence electrons. So in order to fill up our shell, what we need is 3 times 8, or 24 electrons. This leaves us with 24 minus 18, or 6 bonding electrons left. So what we can do is fill that in here. Clearly, we put 2 for each bond, and now we end up having 2 remaining bonding electrons left. So here's where our question comes, because where do we put it? There's absolutely nothing that tells us which atoms we should put it between, because they're both oxygen-oxygen. So let's just arbitrarily put it between these two, in this case here, but actually there's no reason we couldn't also put it between oxygen B and C, so I'm going to draw another structure where we have it here. So in terms of remaining valence electrons, we have 12, so we can finish off each of our Lewis structures. So that's our first structure there, and our second structure there. We could also figure out the formal charges, and obviously the formal charges between these two atoms, they're going to be identical. We're only dealing with oxygen atoms here. So we need to think about what this means, which is the more stable structure, because we have 2 different structures here. In this case, we have a double bond between A and B, and in this case, we have it between B and C. So presumably, if we follow our rules so far, only one of these should be correct. And again, if we figure out the formal charges, let's go through this quickly. We get 0, +1, and -1 for structure 1. We get -1, +1, and 0 for structure 2. So as I said, they're going to be identical in terms of making the decision that way. And what it turns out is experimental evidence tells us that these two structures are equivalent. And by that, what we mean is that they're absolutely identical. And it turns out that this here is not a double bond. It's not a single bond either. It's actually something in between. So if we look at its length, it's actually shorter than a single bond, but longer than a double bond. Or if we look at how strong it is, it's actually stronger than a single bond, but weaker than a double bond. And we find the same thing for these two atoms here. It's not actually a double bond. It's somewhere between a single bond and a double bond. So this is a case where we have resonance structures, or we call this a resonance hybrid. So the reality of the situation is that it's a combination between these two structures. And an important thing to remember when we talk about resonance hybrids is that the structure is not half the time this structure and half of the time this structure. It's actually some combination or some average between the two structures. But since in drawing Lewis structures, we don't have a way to represent that, actually, in some cases you can draw like a dotted line that means a 1.5 bond. But in most cases, we just draw out both resonance structures. And the way that we say it's a resonance structure is that we put it in the brackets and we put an arrow between it. So when you think about resonance structures, some students tend to just get confused and be picturing this flickering back and forth. A good example to keep in mind is the idea of a mule. So most of you know, hopefully, that a mule is a combination of a donkey and a horse. A mule is not spending half of its time as a donkey and half of its time as a horse. We don't see it flickering back and forth between the two. That's not what we see. Instead, what we see is it's an average. It's part like a horse, it's part like a donkey. So if we want to put that in chemical terms, we would want to make sure we put these in brackets here. And remember, this is the resonance arrow. It's not a reaction arrow, it's a resonance arrow. So make sure you mark it up correctly like that.